Let's understand the concept of electromagnetic induction in a simple and clear way. Electromagnetic induction is the phenomenon by which an electromotive force, or EMF, is generated in a conductor, usually a wire or coil, when the magnetic flux, or the magnetic field lines passing through the coil, changes over time. This change in magnetic flux causes electrons in the wire to move, creating an electric current, but this only happens when the circuit is complete. Now, in the diagram shown, there are two main parts, a bar magnet and a coil of wire connected to a sensitive instrument called a galvanometer. The galvanometer is used to detect the presence of current. Let's first look at part A of the image. In this case, the bar magnet is in motion. As we move the magnet toward the coil or pull it away, the magnetic field around the coil changes. This change causes the magnetic flux linked with the coil to increase or decrease depending on the direction of motion. As a result, an EMF is induced in the coil. This induced EMF pushes the charges in the wire, generating a current. This current is detected by the galvanometer, which shows a deflection in its needle. The direction of deflection depends on whether the magnet is approaching or moving away from the coil. Next, let's move to part B of the image. Here, the coil is in motion, while the magnet is kept still. When we move the coil toward or away from the magnetic field linking with the coil also changes. This again leads to a change in magnetic flux, and similar to the first case, an EMF is induced in the coil and a current flows, which is shown by a deflection in the galvanometer. So, whether it's the magnet that moves or the coil, as long as there is relative motion between them and the magnetic field changes, electromagnetic induction will occur. However, if both the coil and the magnet are stationary, meaning there is no movement and the magnetic field stays constant, then no magnetic flux change happens. As a result, no EMF is generated, no current flows, and the galvanometer needle shows no deflection. This proves that for electromagnetic induction to happen, a changing magnetic field is essential. This fundamental principle is the working basis of electric generators, transformers, and many devices we use in our daily lives. So, in summary, the key idea is that motion either of the magnet or of the coil is necessary to create a changing magnetic environment, which then causes electricity to be generated in the coil. This is electromagnetic induction in action.